Hello friends, to another video where we are going to see a paper, such paper where the title is microwave transducer based sensor for real time chemical vapor detection. Here we are going to see a novel microwave transducer based sensor for real time detection of chemical vapors. This was published in IEEE. This approach helps and shows the advantages of microwave technology to offer a sensitive, cost effective, and scalable solution for monitoring toxic compounds in the environment. Let's go. Microwave transducers for chemical sensing. Room temperature operation, where they operate at room temperature, removing the need for high temperature heating, which is a common requirement for traditional chemical resistor gas sensors. Passive device, the microwave transducers are passive devices that mean they do not require external power sources for operation, making them energy efficient and suitable for deployment in remote or resource limited environments. High frequency wireless operation. Operating at high frequencies allow for wireless communication and data transmission, enabling real-time monitoring and remote sensing applications suitable for networking and communication. Transducers can be easily integrated into existing wireless networks, facilitating data sharing and communication between multiple sensors. Differential passive microwave resonator based sensor. Enhanced sensitivity. This proposed sensor uses a differential approach with the two microwave resonators, one is serving as a reference and the other incorporating the sensitive film. This differential design enhances sensitivity by minimizing environmental variations and focusing on the specific response of the sensitive film to target vapors. And what is sensitive films? That is the film is composed of Perotrpes, PSSM, WCNTs, composite material that is chosen for high sensitivity to chemical vapors. This material exhibits changes in its electrical properties like permittivity, conductivity, and other things upon interaction with the target vapors, enabling detection. The sensor design and theoretical model. Resonator design. The sensor incorporates two band pass resonators. They're designed to operate within the 126 range gigahertz frequency range. These resonators are crucial for detecting changes in electrical properties of the sensitive film when exposed to target vapors. Reference and sensitive channels. One resonator serves as a reference channel, providing a baseline measurement to compensate for environmental variations. The other resonator, known as the sensitive channel, incorporates the PSSM WCND's composite film, which interacts with the target vapors and alters resonator's electrical properties. Now, simulation results and analysis. Simulation tool that is used. The behavior was simulated using HFS STM finite element tool, which allowed for detailed analysis of the sensors respond to different situations. Simulation parameters that considered various things, including properties of substrate, that is paper, silver nanoparticles, and sensitive film. Experimental setup and results. Fabrication and testing. The sensor was fabricated and tested with ethanol vapor. Two devices with varying layers of composite sensitive film of 5 and 50 layers were investigated. Sensitivity observations. The sensitivity of the sensors was observed in terms of resonance frequency and magnitude shifts of the parameter. Ethanol vapor concentrations ranged from 500 to 1300 parts per million. The discussion of sensitivity and limitations. Positive frequency shift. The sensor exhibited positive frequency shift in response to the ethanol vapor that indicated the increase in electric constant of the sensitive magnitude shift. The sensor also displayed the shifts in the magnitude of the S parameter that shows changes in the impedance of the sensitive film, and the negative frequency shift that suggests a decrease in the dielectric constant of the film. The future improvements and directions. Addressing limitations focus on mitigating continuous drift and enhancing sensitivity. Further explore material properties and their impact on sensor performance. Optimize structural design and implement chemical functionalization. Explore integration into real-time multi-sensing platforms for the Internet of Things. And the conclusions were: the proposed microwave transducer-based sensor demonstrates potential for real-time detection of toxic vapors, offering a sensitive, cost-effective, and scalable solution. The limitations were continuous drift and enhanced sensitivity, exploring new materials and optimizing fabrication processes. Sensor holds promise for integration into real-world applications, including environmental monitoring, industrial safety, and Internet of Things. The conclusions led to a major drawback to that gave the future directions and helping in developing more knowledge on the topic. Thank you for giving me your time.